Welcome to Lecture 24B, which is the second in the series of lecture in this lecture section. This again, Stokes theorem 3D tooling example, and this is material covered from reading assignment 4, section 4.2.1, and the objectives are similar to skills for applying Stokes theorem to geometrical problems. And the concepts, conventions, and visualization skills will include closed contour encloses a surface, the direction of the surface area vector, and the direction of traversal of the contour are related to each other by the right-hand rule. Okay, so this slide is the usual one, except I'd like to make a note of the fact that these questions that we'll be looking at in this video should be attempted as homework questions before you watch the video. Only watch the video for these examples if you're having difficulty. So the question that we'll look at first is question 15 from chapter 17.7. And you're given the vector field as shown, and also a contour, which a circle, the position vector being x, y, z, and the x, y, z parameterized take on the values 3 cos t, 4 cos t, 5 sine t respectively. And this is represented by the solid blue line that you see here, this blue line. And this is valid for t between 0 and 2 pi. And the question's asked to compute the right-hand side of Stokes theorem, which is in fact the part that's indicated in orange. So we'll need to compute the curl of the vector field and also the surface area, the differential surface area, but of an area which is to our liking, in other words, something that's relatively simple to calculate. All right, so our starting point is to recognize that if we were to compute the magnitude of the position vector squared, that means x squared plus y squared plus z squared, then you would end up basically with the value equal to 25. So x squared plus y squared plus z squared equals 25 is actually the equation of a sphere. And so that's the area that's shown in light blue, this equation of sphere. But the position vector basically traces out a circle, and that circle lies on that sphere. So that's basically what we see indicated here, and the radius is equal to 5. All right, so the simplest enclosed surface associated with this contour would be an oriented disk of radius 5, and that's the part that's shown in terms of olive green, in terms of color. One could have actually taken a hemisphere part, but that would have been a little bit more complicated if we're going to apply Stokes theorem. This olive green disk and this portion of the hemisphere of sorts share the same boundary. That's this contour that you see here. Okay, so the next thing then to say is, having decided that we're going to use this disk here, is the parameterization of the surface. And so the simplest thing is to realize that the outer bound of the surface is the line. And so if we were to multiply the position vector by some new variable v, as shown here, and let v range from 0 to 1, then all we'd be doing is basically mapping out the whole space enclosed by that contour. So this is a suitable means of parameterizing the section shown in olive green. Again, t is between 0 and 2 pi, and v in this case would be from 0 to 1. All right, now that we've done that, we can compute the curl of the vector field. And so having done this now many a times before, I just state the result as shown here. The differential surface area would be basically to take the partial derivative of the position vector with respect to v, and also take the partial derivative with respect to t, and then they take those two vectors, take their cross product, dv by dt, which is what we've done here. So you end up with the result 20v minus 15v, 0, dv dt. Okay, so we have the position vector, surface area vector. We also know from the information provided that this position vector traces out this line in a counterclockwise direction. So if this is in a counterclockwise direction, that implies that by the right-handed convention, if you put your right fingers in this direction, and the thumb points in the direction of the differential surface area vector, which would happen to be in this direction. And so what is the appropriate direction? Well, that's shown here. TDS traverses circle in a counterclockwise direction. Therefore, NDS is going to be pointing in the x and minus direction, x and minus y direction. So let's go back and look to see if that's the case. Well, yes, this is going to be minus direction. And so effectively, we've chosen the correct direction for this vector. Had this been the wrong direction, then we would have taken this and multiplied by -1. And that would have basically turned this arrow the other way around, so it's pointing in that direction. All right, so the next thing to do is to take the curl of the vector. We know basically what the position vector is, so the z value we can pick off from here, and the y value we can pick off here, and we end up with this being the curl of the vector f in terms of the variables t. This is the differential area vector shown here, and the bounds on the integral basically are the bounds that we obtained from here. T is from 0 to 2 pi and v is from 0 to 1. So integrating with respect to v first and then with respect to t. Anyways, if you do this integral, you get basically the value that's shown here, which is 15 pi. Okay, so the next thing basically is to look at another problem. This is question 19, it's chapter 17.7. Stokes' theorem for evaluating surface integrals. You're given the vector field f, which is 2y minus z and x minus y minus z. S is the cap of the sphere x squared plus y squared plus z squared equals 25 between x of 3 and 5, excluding its base. All right, so it's only the portion basically that involves the cap itself. And we're asked to evaluate the line integral in Stokes' theorem to determine the value of the surface integral curl of f dot nds. And we're going to assume in this problem, as part of the problem statement, that n points in the outward direction from the sphere. All right, so this surface that you see here is this is the outer portion of that dome, and this is the NDS that's pointing out. All right, so we know by convention, if we're given that NDS is pointing outwards from the sphere, then by the right-hand rule, TDS will have to be going in this direction. And so if we wrap our fingers in this direction, that points in the direction of NDS. All right, so we basically just applied convention to understand what the direction of TDS would be. All right, so we need to basically determine what the boundary is going to be. And so it's the intersection line between the sphere and x equals 3 plane. All right, in the x equals 3 plane, we just substitute in for the equation of the sphere, value of 3, and we end up with an equation of z in terms of y. And so this is just a circle. And of course, this circle basically is parallel to the yz plane, but it's located at x equals 3. Okay, so this is this slightly bluish thing that you see here, purpley color. That's the circle, which is this, but it's at x equals 3, so it's sitting out here somewhere. All right, so now we need to know what the position vector for the intersecting line is. And so for x equals 3, that puts it out here. And then we're just basically tracing out a circle. 4 cos t, 4 sine t, 0 less than equal to t is less than equal to 2 pi. If you basically go from 0 to 2 pi, then you'll find out that you're actually tracing the circle in this direction, and that's consistent with the right-hand rule. The tangent vector basically is just going to be the derivative with this with respect to t, and we end up with this expression here, which is in fact the TDS that you see there. All right, note that NDS is pointing outwards from the spherical cap, and TDS is parallel to the YZ plane. So as we said, TDS must be in a counterclockwise direction by convention, and the plane's orientation is in the x direction. All right, so effectively, like I said, we can choose to integrate over this dome surface, or we could actually use this planar surface bound by this blue contour. But in that case, if we're going to use the surface, we've got to make sure that the area vector is pointing in the right direction, and this is the right direction, which is in the x direction. All right, you can access this figure at this link here. So now we can basically do the left-hand side of Stokes' theorem. So it's f dot TDS, f dot r dot t. Here basically is the f vector, and so the f vector would be a matter of just taking this and substituting the x, y's, and z values from basically the parameterization of the position. So we can substitute that in, and this now becomes only a function of t. And this represents basically the TDS vector, which is this one that you see here. If you take the dot product of these two, you end up with this integrand. If you take the integral of this, you'll end up with a value of 0. All right, so another question, question 41 from chapter 17.7. It's a compound surface and boundary. We begin with the paraboloid z equals x squared plus y squared for 0 is less than or equal to z is less than or equal to 4, and slice it with the plane y equals 0. So that's basically the back surface that you can just see in the sort of a shadow form. I'm going to let S be the surface that remains for y greater than or equal to 0, including the plane surface in the xz plane. And so we have this outer perimeter, we have this top surface, and we have the back surface. So we actually have three different surfaces there, basically constituting the object that you see here. So we're going to let C be the semicircle and line segment, that's this semicircle, line segment, that bound the cap of S in the plane Z equals 4. So this basically is in the plane Z equals 4, and you can see that this is going in a counterclockwise direction. And F has this particular form, 2z plus y, 2x plus z, 2y plus x. Three parts of the question. First is describe the direction of the vectors normal to the surface so that we're consistent with the orientation of C. Second is to evaluate the curl of F dot the differential surface area over the surface area by computing the curl of F and appealing to symmetry. Symmetry meaning we can probably simplify the integral if we find that there's either an odd or an even symmetry. And finally, evaluate F dot dr and check the agreement with part B. So we're going to basically do the right-hand side calculation and we're going to do the left-hand side calculation. And the two results should be similar. This is very much similar to what we did in the last lecture, that is lecture 24A. All right, so for part A, I basically just drawn it out a little bit more. So part A was to describe the direction vectors normal to the surface that are consistent with the orientation of C. Well, the orientation of C was counterclockwise. So by the right-hand rule, right, the area vectors should be basically pointing outwards, okay? Outwards meaning basically in this direction from this back surface and from the paraboloid surface in this direction, okay? So it's on the inner bowl, it's pointing outwards from the surfaces on that inner bowl. And so that's how it's being marked here. So this is just a summary. The direction of the area should be in accordance with the right-hand rule. Fingers pointing the direction of the contour traversal, and the thumb points in the direction of the surface area vectors. So that means for the planar section, on the xz plane, the surface area vector points in the positive y-hat direction, and on the half section of the paraboloid, the surface area vector points in the negative y-hat direction. So it's important to know that because when we do the actual calculation of the surface area vectors, we have to basically check to see that y-hat on one case is negative and y-hat in the other case is positive. All right, so this is now the detailed calculations. First thing we're going to evaluate is to do this calculation. This is for part B. So we need to do the curl of the vector field. If you do that, you'll find you end up with this answer, which is just a constant. So it's pointing in a particular direction, 1, 1, 1. So what we need now is the surface, differential surface area for the plane surface. All right, y is equal to fzx and y equals 0. Okay, so that's basically the planar surface that was on the back side. So we can use the explicit representation to compute NDS planar. Now notice here that this isn't in the standard form that you're so used to, where z is a function of xy. Here, y is a function of zx. You effectively just treat it exactly the same thing, but when you're taking partial derivatives now, you're taking partial derivatives with respect to y. So y partial x and y partial z. The only thing is where to put it. So if it's y partial x, this is the x component of the vector field. If you're dealing with the z component, well then it would be here, y partial z. The y component will be 1. Okay, so this is consistent with what we did when we said this was z as a function of x and y. And this will be dz dx. Now, we've put it in this fashion. Why? Because we know when we plug the numbers in, we get 0, 1, 0. And this is pointing in the y-hat direction, which is consistent with the right-hand convention. So we've chosen the right direction. Had this been the wrong direction, we would have multiplied this all by -1. We also need to know the bounds on the surface, and the bounds basically on the upper bound is 4, which is z equals 4, and the bottom bound is the parabola, which was x squared. And x can range from -2 to +2. So this sweeps out the parabola, which is sitting on the y equals 0 plane. For the paraboloid surface, we have z equals x squared plus y squared. Again, we can use the explicit representation to compute n ds parabola. And in this case, it's in the standard form. Z is a function of xy. This is minus zx minus zy1 dy dx. And when you take the partial with respect to x, partial with respect to y, you get minus 2x minus 2y1. Right? And so you would ask yourself again, is this in the right direction? And it is, because for positive y, this is pointing in the negative y hat direction. So this is the right representation of the surface area vector. What are the bounds going to be? The bounds are going to be y equals 0. And y is square root of 4 minus x squared. And the limits are between -2 and +2. So this basically describes the outer parabolic surface. All right, now that we have computed the curl of f and the two surfaces, we can basically do the computation of curl f dot n ds. And because the boundary we've chosen are the back surface and the paraboloid surface, bounded by the contour, this basically is the sum of two contributions. Contribution of the planar surface, contribution of parabolic surface. And so all I've done now is to take the first term, make use of the curl of the vector. This was the differential area vector for the planar, and then do the integrations. Bounds are already included. They basically have come from here, and you get 32 over 3. For the parabola, basically, we have the bounds here. They come from here. You have the curl of the vector, which is the same one, and this represents the differential surface area vector, which comes from here. If you do this integral, right, you'll end up basically with an answer of minus 32 over 3 plus 2 pi, and for this one, it was 32 over 3. All right, so you might ask yourself, how did we basically get these results? Well, we used the substitution x equals 2 sine theta dx 2 cos theta, and the trig identity cos squared equals 1 plus cos 2 theta over 2 to solve the square root component term. And so we have basically this term here that had to be solved using this substitution variable technique. And so I've just shown out in detail how that was done here. All right, so the final answer is to take the sum of these two values. 32 over 3 was for this component, and minus 32 over 3 plus 2 pi was this one, and the answer we get is 2 pi. So the next step basically is to evaluate the left-hand side, and then check that we have agreement with part B. So I'm going to avoid confusion, we're going to just replace the symbols dr with ds, because r is used in another context. The position vector r1 for the semicircular portion here is 2 cos 2 sine t, 4. 4 because we're lying on the z equals 4 plane, and we're going around a half a circle, so t is going from 0 to pi. For this line segment, we're going from -2 to 2, and so the parameterization of that line is t0, 4. Again, 4 is because it lies on the plane z equals 4. And so if you follow this, you're going from most negative to most positive, going across here. You're going from most negative, in this case 0, to pi, which means you're going around this way. So everything is consistent, so this is the correct means of parameterizing these two line segments. We need the differential tangent vectors, so you have to take the derivative with respect to t, dt. r prime dt takes on this form, and r2 prime dt takes on this form. We call this ds1, we call this ds2. And so the closed contour integral would be f dot ds is contribution of this circulation and contribution of this circulation, which is what we see here. All right, so f dot ds1, what is f going to be? Well, we have to take the value of f that was on the previous page. We have basically x, y's, and z now in terms of the parameterization. 2 cos t for x, 2 sine t for y, and 4 for z, and make the substitution in for f, and we end up with this term here. The r dot t, r1 dot t, which is this one, basically comes from here, which is here. And then you just take the dot product and you end up with this very long expression here. You integrate this and you get minus 32 plus 2 pi. For the second contribution, which is along this line here, we have f evaluated, but this time at values which represent values along the line. So that x becomes t, y becomes 0, and z becomes 4. And so this is what we end up with f. And the line element would be this one here. Take the dot product and integrate, and we get 32. The final solution is to take the sum of these two, and we end up with 2 pi, which is essentially the same answer as we had when we dealt basically with integrating over the surface. So that concludes Lecture 24b. Thanks for listening.